So for this project, we decided to use a heat exchanger to model convection and conduction analytically and numerically. We chose this project or this design and topic due to its applicability in industry. Since natural gas is a very common fuel used around the globe, it must be transported and used worldwide. So a heat exchanger is very necessary for the liquefaction of the natural gas. And for this design, a lot of assumptions had to be taken into account. For example, the number of tubes inside of the pipe was calculated based off of parameters set for dimensioning the heat exchanger itself, and the length of the heat exchanger was found by other resources online that show common heat exchanging problems in industry. The heat exchanger that we used is a shell and tube heat exchanger. This is not exactly what is used in industry, but it gave a good assumption of what the general application would look like. To begin the cooling model, I ran the Aspen predictive test inside of Aspen with this heat exchanger right here, and I used liquid nitrogen to cool incoming natural gas, which in this case was assumed to be methane. This is not a great assumption, but it could be a good assumption if a separation process was implemented prior to the feed of the heat exchanger, and in which case the majority of the composition would be methane, and this would be a good assumption. This analysis was ran to obtain values and correlate them with online research values and other values found in tables, which can be seen in the references. But to solve to get some convective data, we used the inlet temperatures and outlet temperatures, as well as the average temperature for the entire heat exchanger, along with properties listed here that were found in tables from our handouts in class. We then calculated a volumetric flow rate, a Reynolds number, and a Nusselt number so that we could get a heat transfer coefficient for the overall, or not the overall, but the system when looking at methane. And then using this information, we could then calculate other values, but also along with this, we were able to calculate the overall Q, and that was just represented by the mass flow rate times the heat capacity, and then the differentials and the entering and exiting temperatures. We then could find an overall Q for the total shell and tube heat exchanger by multiplying by the number of tubes inside the heat exchanger. Following this, an overall heat transfer rate was wanted to be found since we were using heat exchanger, and is given by this equation right here, where the U0 is the average, not the average, but the representation of the heat transfer coefficients for the inner and outer surfaces, as well as the conductivity of the pipe itself, which is made up of aluminum. The delta T log mean was also needed to be calculated for the overall transfer, and a final value was able to be found for the convective rate of transfer. After this, the analytical modeling of conduction was put into place, and conduction was only seen inside of the pipes themselves on the aluminum side. So we used this Q equals K times A delta T to solve for a conductive Q for the pipe. And then that was also multiplied by the number of pipes to get a overall conductive solution for analytically solving the overall heat transfer. Along with this, a numerical model was also run in COPSOL. The model, as you can see here, did not turn out perfect and was not represented 100% correctly. Even though the design was specified to be a cylinder, the results were given in a cubic formation. I'm not exactly sure why this is, but it still gave a overall good representation of the heat in and heat out of the pipe, and showed temperature profiles of the pipe. As you can see from the previous picture, there was a hot fluid going in, and in this picture, even though it's not the greatest representation, you can see that everything has been cooled down by the exiting of the shell. Note that this is just a representation of one of the shells inside, or one of the tubes inside of the shell, and was just a model to show how an individual tube would work with this. In order to do this, we had 3 separate cylinders inside of the COMSOL representation, where one of the cylinders was the fluid inside of the pipe itself, which was considered methane in this case, and then on the outside there was a tube that was classified for the aluminum, and then on the final cylinder was made up of liquid nitrogen, and which can be seen keeps a pretty constant temperature profile across here. The COMSOL data was then transported to Excel, but there was a lot of nodes that were in this 3D model, making it very difficult. So a graph was represented of all of the different temperature variations throughout the design of the surface, so the aluminum itself. And with this, convective or conductive heat transfer could then be calculated using these values, but these values were specified with values that were solved in or found in the analytical approach. So solutions are identical and numbers are also identical. All in all, the project definitely showed to be very helpful in understanding heat and mass transfer, but also a problem was seen, or not a problem, but other solutions could have been referenced, which can be seen right here, where we have a spiral heat or cryogenic heat exchanger, which is mainly used in industry. However, we were not taught how to deal with these types of heat exchangers, although I don't think they would vary too much, other than that the pipes inside have a longer length than the actual pipe themselves, so that would have to be considered in calculations, as well as there is a lot of void space inside of the exchanger itself for more pipes or more fluid to allow for further cooling or heating of the fluid. Thank you so much. Hope you enjoyed my project and enjoyed being in your class.